Hello, we are Team Granular, and we are trying to answer the research question, how do we create a bio-inspired salamander robot that can move through a granular media using foldable robotics techniques? So let's dive into that. So first we wanted to look at, the inspiration behind this creature, which is the salamander. Salamander is a really interesting specimen because one, it is able to traverse over so many different types of media. It's able to go from solid ground to sand to mud and even swimming in water. So it's able to very effectively traverse over a wide range of medias, which has made it really interesting from a biomechanics perspective. Many teams have also researched salamanders as well. A lot of the research teams that's focused on in the past has really focused on that actuated spine motion, which kind of resembles, the motions that, you would think of associated with like a snake, as it is able to curve its entire body basically, especially with the added motion of the tail. On the right, we have a list of parameters that we collected from literature on the actual salamander itself. This includes, typical information such as, mass, stride length, the actual muscle output, and stuff like that. So that's all seen here in the table. You can look at it at your own discretion. Basically, our proposed mechanism has basically two main mechanisms involved. One, the actual spine actuation, and the one is the actual limb actuation. So for this, it basically will require a total of 4 servos, 2 for the actual limbs and 2 for the spine motion. The goal is to basically achieve a C shape when the robot is at its two extreme states, with the feet hitting the ground on those C's, and you'll be able to see that hopefully a little better in the kinematics section as we dive into that. So we divided kinematics into 2 main sections. Seen on the left is the actual limb motion we have right now. We are assuming that our actual end effector is basically at this joint C right here. So you can see as it moves, it'll touch the ground here. Right now it has kind of just a spring damper effect on it, which will be refined into the actual motion that we will see, that kind of resembles the salamander inspired limb motion. On the right, you have the spine right here. This is what we mean by the C shape. So basically when it makes those C's, the limbs will touch the ground here and here. This one has a couple different, segments on it, but that's the main motion. From our calculations, we have determined that the torque on the end effector, the input torque necessary to achieve the desired motion, is about 0.021 Newton meter. We calculated this using the fact that a salamander is about 0.33 kilograms, but one limb only holds, about 0.4 of the weight. And so from that, we were able to determine that it really needs, for forces, it only needs 1.3 newtons, and from that we were able to calculate the torque input. For future plans, we plan on refining our kinematics/dynamics models to reflect more the actual overall motion that we want to achieve. After that, we want to actually integrate the spine and leg motion together, figure out how they actually work together and affect one another. Kind of accompanied that stretch goal would be to reduce the number of actuators. Right now, we utilize 2 in the front and 2 in the back for spine and limb actuation, but I think it is feasible to be able to combine kind of those motions together. After that, we need to identify the main parameters that we want to test and determine. This includes such as materials, stiffness of materials, the actual actuators that we're going to be using and stuff like that. And then after that, we're going to build our first integrated prototype. Understandably, we'll probably go through an iterative process here to, really refine our prototype, and then we will test our system in granular media, probably Critcrete, which is a type of sand. So yeah, that is our progress. Contact us if you have any questions.